So, um, real quick, let's go over some housekeeping. I had a question about uh, the homework. So the one that's due today, that's supposed to be a process flow diagram, which is basically just a higher level overview. It's just your unit ops and streams. It doesn't really include details about instrumentation and piping dimensions and stream compositions. It would just be like incoming stream, pump, pump feeds a reactor, reactor feeds a distillation column, and then you have outgoing streams from there. The reason I did that is because that's what you'll actually use in class at Davis. You won't need to make a full P&ID, which has super fine details of like how you connect to your control system and your piping dimensions and specifications and all kinds of stuff. So if I wasn't clear on that, I apologize. I want you guys to be aware of P&IDs so that if you, in an interview, they ask you about it in context of this class, you can at least explain that, yes, you know what that is and you know what it's supposed to look like. But we don't really have the time this quarter to spend a lot of time developing P&IDs. And quite frankly, if you can work with electrical schematics, you can work with P&IDs. The CAD skills are the same. It's just P&IDs are also time consuming, and we only want to focus so much on CAD skills. We're transferring into controls and ladder logic now. So hopefully that's a clear explanation of what's going on with that. Let me know if you have any questions. The other thing I want to do before we get into ladder logic today is you should be able to see my screen with the Google Drive up. So this is our shared drive with all our stuff in it. There's two things. The first one is I want to call your attention to the reference materials. This is a bunch of files that I've either developed myself or found from other places. So I think I sent out an email with an announcement about this P&IDs presentation that I found. This is a pretty quality stuff. I probably should have just presented this instead of what I did. So if you want more information on P&IDs, you can look at this. There's a terms and definitions file that I'm periodically trying to update, as well as this external references file has links to like YouTube channels and stuff. If you want to check that out. I haven't updated that in a long time, but I'm going to try. And then the last thing in here, there's this instrumentation folder. This has a ton of really, really high quality documents in it. Some of it's pretty technical and has to do with like data transmission and control systems. So like Profibus PA is a industrial network standard. Heart communication is how smart instrumentation in the field communicates. It's really interesting, fascinating stuff, but probably pretty far out in left field for you guys. But then there's interesting stuff like level measurement and control valves and why you get cavitation in control valves. And this is really, really, really good reference material for when you're in like 158B. So just keep in mind that this is here. It's available for you. You can grab it at any time and take a look. And then if you're trying to find more information on anything in the controls process engineering area, let me know, and I can either point you to the files in here or maybe try to help you find a resource online. But just be aware that that's there for you, and I highly recommend you take a look at it because there's really interesting stuff. Okay, the second thing I wanted to talk about in this drive is if you go to the PLC programming folder, there's this PLC slot rack layout. And that's what we used in that previous video to manually configure the PLC rack setup in our Click software. So that was the first tab here, the rack layout. It's got a nice little picture of the PLC and what each module is with a description. That's good reference info. today I created a second tab called IO index. And what this is a quick kind of high level description of what's wired to what in here, and what memory location it's referenced to. So on the rack layout, you know, slot 0 is the actual PLC. So on the IO index, you go slot 0 PLC, what's connected here. And this is actually, I got to update this. This is actually C3. But anyway, it's got a quick description of what's wired to it. So hopefully this will help you guys in the exercises we do going forwards. You can reference this index and know what your memory bits are associated with. So for example, the indicator lights we have on this panel, one second. Give me 2 seconds here. Okay, so these indicator lights right here, you guys can see that the shot of the panel, right?
Yep.
Yep. Okay.
Yep.
Cool. So like the Y001 through 4, those are wired to this on the PLC. So I've also actually labeled them with tape on the panel. But you have this index too. If we're not live programming, if you're like programming offline, you know what's wired to what. So I'm pretty sure this is all up to date and accurate to how the panel's wired right now. Oh, by the way, NC means not connected. So there's a bunch of stuff in here that's not connected. If we add any more wiring or wire anything new up, we need to update this. So going forward in future years, whoever's running the class needs to make sure and stay on top of that. But I just want to make you aware that that's also available, and we'll be probably referencing that as we go through these exercises. Okay, so without further ado, hopefully y'all all have your Click software fired up. If you don't, go ahead and get that fired up. And I'm gonna switch over which screen I'm sharing here. Okay, so you should see Click software and an external shot of the panel with my hand waving in front of it. You got that?
Yeah, we got that.
Okay, awesome. So what we're gonna do today is continue talking about what we started yesterday with counters, and also we're gonna control the actual motor that we have. So real quick, I'm gonna give a brief overview of the hardware that we got. Sorry for all the screen switching. I'm really trying to do my best to not get you guys seasick, but unfortunately we got to jump around a little bit. Okay, so inside the panel, we have this box here, which is a VFD, which stands for Variable Frequency Drive. And what that does is it changes the frequency of an AC waveform that's outputting to a motor. And by doing that, it basically changes the speed at which the motor runs. So we're going to be controlling this motor right here. It's on my bench. And so that variable drive can output between 0 and 60 hertz. So 0 to 60 cycles per second, which is what hertz is. Okay, and that's output to this motor, and this motor is rated to spin, I think it's 1750 rotations per minute. 17, yeah, it's rated to spin at 1725 rotations per minute. So basically, the way this is set up, 60 hertz should equal 1725, and 30 hertz should equal half of that, and 0 hertz should equal no spinning at all. Okay. Now, the other part of this that we have here is you can see this kind of like football goalpost looking thing here. This is a fork sensor. And can you see the base of it there? Yeah. So you can see when I break the beam with my finger, my finger gets hit with the laser. You can see this lights up here. So you see how that works? That's wired into an input on the PLC. And what we're going to be doing with that is, as this motor spins, you can see my super high-tech signaling device breaks the beam on the sensor, and we'll be able to pick that up with the PLC. So what we're going to try to do today is write a program that both controls the speed of this motor and also measures the speed of this motor by counting how many times per second that beam gets broken by this little flag. Okay. So I'm gonna leave that view there in the bottom right hand corner so we can kind of monitor that as we go. But we'll mostly be looking at the ladder logic today. Oh. Why is that going away? That's not good. There we go. Bear with me, I'm still learning these technologies. So we made something that kind of looked a little bit like this last session. But I think the best thing to do is I'm just going to actually take a screenshot of this, and then we're going to make this from scratch. So just so I have a reference of that. This way I can explain what we're doing as we're going along, instead of trying to get you guys to reverse engineer what I've written here. Okay. So the first thing we need to do is set up a run command to the VFD. So if you pull up the IO index for the PLC, and you look at slot 0, Y005 and 006, those are the VFD run and the VFD stop. And so those are discrete outputs from the PLC to the VFD that either tell it to stop running or that it's allowed to run. So we need to wire up some a latched bit for the run and an interrupt bit or for the stop. So what we're going to use is, if you look on that on the index, X103 is our green button, and usually green means go, right? So we'll use that for our start command. And what we're going to need to do is set up a latched configuration like we did last time. So we'll make our output be Y005 because that's our run command to the VFD. And then we'll make our parallel latched bit Y005. So that's self-latching, right? We went over this last time. And then we need to make our interrupt to stop that latch. We need to pick something that makes sense. Now, if you'll remember back to what we talked about last time, we need to have an up and down input for the counter. So that's 2 buttons. We need to have our start button, which is 103, and we need to have an interrupt button. So what I'm going to do is I'm going to use the E-stop button as our interrupt. And we know that that's X104. So that E-stop button is this mushroom button right here. If you look down in the bottom right, we've talked about this before, that latch is closed when you push it and it stays closed. So that's a good thing to use for stopping a motor, right? Because you don't have to worry about any fancy programming, because when you hit that button, it'll stay physically closed. And so you can just use that as a straight interrupt. So that's what we're going to do on the next rung. We're going to write a normally open, and we're going to use X104, which is our E-stop. And we're going to use that to activate Y006, which is our stop command to the VFD. So basically, all I know that when I hit that E-stop, it's gonna close this X104, and it's gonna tell the VFD stop running. Okay, so now we have our run command and our stop command configured. So just for grins, I'm gonna go ahead and I'm gonna write this into the code or into the PLC, just so we can test it out and see, make sure it works the way we want to. Okay, so we're written in. We can see this normally closed is good. I want to move this, move the camera and actually open this panel real quick. Ooh, y'all probably aren't going to be able to see those lights very well. All right, let's give it a shot. So I'm going to hit the start command. Okay. So you can see in the code that Y005 is now lit up. And if you look very closely at the VFD, you'll see there's a green light on here. And that means that that means that it's getting a run command. So that's good. That means we're in business. So now let's test our stop circuit. So I'm going to push the E-stop. Okay, cool. So if we look at the code, we see this normally open contact got interrupted. That's good. And then we see this normally open contact is now closed, and that's energizing our stop command to the VFD. That's interesting. So if you can monitor those lights up there, hopefully you can actually see it. Sorry, I don't have a better view angle on that. Okay, so the point of that is we know that's working correctly. We're happy with that. Okay, so the next thing I want to do in this program, I'm going to delete that end rung, is the kind of some of the more complicated stuff we worked on last time, which is this counter. Right here. Oh, you can't see what I'm looking at. So if you remember from last time, we used an up-down counter so that we can set the VFD speed. And ultimately, we're going to write that into the analog output that's going to this VFD. So I'm going to grab a counter on our instructions list, and I'm just going to assign that to the first open counter bit, which we don't have any code in here. So our first open counter is CT1. I'm going to make this an up-down counter, and I'm going to set the set point to 11. So if you remember from last time, we're going to have this counter go from 0 to 10, and that's going to correspond to 0 to 100% output on our VFD. So I'm going to put the set point at 11 so that if somebody tries to make the motor spin faster than it's actually physically capable of spinning, we'll have an alarm. Okay. So I got that done. I'm going to go in here, and I need to draw rungs connected to my counter. So playing around with this software, something I figured out is if you want to just draw a rung all the way across, just select the first spot in here, highlight it, and then click on the draw, and it'll give you that option to just go all the way across. So I want to draw 2 more rungs. connected to the down and the reset on this counter. Okay, so now we're going to do the same thing we did last time, where we're going to configure these two buttons here, the white and the red button, to increment up and down on our counter. So I'm going to make that X101 is my white button. I'm going to make that the increment up on the counter. And then I'm going to make X102 the increment down on the counter. And then I'm going to make my E-stop be the reset for this thing. So why would I set that up to have the E-stop reset the counter?
It sets the speed to 0.
Exactly. So if I have an emergency stop button, I want to make sure that that kills everything, and that's a really good way. We already have it to set up to tell the VFD to stop, right? But this is an extra layer of security where I reset my VFD output to 0 also. So not only is it being told to stop, but even if that stop command didn't work for some reason, it also is being told run at 0. So it's not going to spin at all. So it's kind of an extra layer of safety. And we basically get that for free because we needed a way to reset this counter to 0 anyways. Well, I guess we didn't absolutely need it, but it's a nice to have. And so it just kind of like, for multiple reasons, it all works out really well to just set it up to where your E-stop resets your counter to 0. Okay. So that's just something to be thinking about as you're programming in here, like why you're doing things that way. Okay, so the next thing we need to do on here is we need a way to write that counter value to our analog output, to the VFD. So if you look in your index for the PLC, that analog output, if you look at slot 4, channel 1, which is VFD speed 4 to 20 milliamps. Okay. Now, if you're not sure where that is in our data registers, you can go to setup and system configuration. And unfortunately, you're not going to be able to see this on my screen, but if you do this on your software, you'll be able to see it. If you go to IO4, you'll see that the output is DF5, 6, 7, and 8. And so we can sort of deduce that DF5 is associated with channel 1 on this analog output card. Okay. So what that lets us do is we can put in a math bit here. And so in this math bit, what a math bit does is it writes some value into a data register. And so we want our data register to be in this result field here, okay? And we could go searching for it in our huge index of things, right? And we can see that DF1 through 8 have been assigned. But I know, based on looking at the index and looking at my system configuration, that the analog output for the VFD is going to be DF5. That value in memory is what's being interpreted and changed to a physical analog output, a 4 to 20 signal from that card. So that's going to be DF5. So I can just write that into that result field. I don't need to worry about searching and figuring out anymore. I already got that figured out. Okay. And then on the math side, if you remember last time I talked about our scale for that output signal is 0 to 100, right? And our counter is running from 0 to 10. And so I'm going to write a little math function that takes that counter value and multiplies it by 10, so that basically every increment of my counter is a 10% increase in my VFD speed. Okay. So my counter value, if I look at this counter block here, this counter block right here. Oh shoot, I just realized you guys can't see that pop-up screen that I'm working on. This is a problem. Okay, I know how I'm going to take care of this. So what we're going to do is I'm going to have to keep swapping back and forth which screen I'm sharing, which is kind of a pain, but it's what we got right now. So I'm going to play with this more in the future, and try to get a better working solution. But right now I'm just going to have to toggle between screens as we're doing this. Okay. So I'm going to re-talk about everything I just said because you couldn't see the pop-up screen that I was talking about. So I'm going to write a math block in here, like I said before. And you guys can see that pop-up screen of the math block now, right?
Yeah,
Okay. And you could not before, right?
correct.
Okay. Sorry about that. Still figuring out the tech. Okay. So in this result field, this is the data register that stuff gets written into by this math block. And so as I talked about before, DF5 is our analog output. So I'm going to write that in the result field. Next time I'm talking about stuff that doesn't make sense, yell at me. And then in the formula side, I know my current value for my counter, just looking at that block, is going to be CTD1. Okay? And I'm going to scale that so that one increment of that counter is 10%. And I'm just going to do that by multiplying it by 10. So as you can see, you can do all kinds of complex math in this math block. But what we're basically just using this to take a value from one point in memory and assign it to another point in memory and scale it, right? So there's actually another function that does this, which is the copy function. And you can see here, there's all different kinds of copies where you can do single, where it's just a one-to-one, writes one from another, or you can use a fill where it takes the value of one point and writes it into a whole bunch of different points in memory. But the limitation on this is you can't do any manipulation to the value when you do a copy. It's just a straight take it from here, put it in here, right? And so what we're doing is we're kind of being sneaky here, where we're using a math block to do a calculation, right? But we're also using it to do a copy operation. So it's just more efficient programming, right? Because what we could do is we could use this math block to say, okay, I'm gonna do that scaling operation, write that new value into some point in memory, and then I could use a copy to copy that value from some point in memory and write it out. And it might make sense to do that in certain areas, but for us, this is a really simple program. This is the way we're going to do it, because it's easy and simple, and it's easier to follow. Okay. So this looks pretty good. I think this program will run as is. Now there is one thing that I forgot to do already, that some of you from last quarter might know. Does anybody know what I'm forgetting that will prevent this program from running?
Writing it back in.
What's that?
And
What was that?
end.
Oh, yeah, that's true. I also forgot the end. Good catch. So one thing about the way we have this panel physically configured is that there's a motor contactor in the panel, and basically it's kind of a fancy relay, but it has to be activated in order for this in order for the VFD to actually turn on, or not for the VFD to turn on, but for the signal. It's wired downstream from the VFD, so the signal from the VFD gets output and it goes through that contactor and then goes to the motor. And so if that contactor isn't engaged, the VFD will output power to the motor, but that contactor will prevent it from getting to the motor. And so if you look in the index again, the motor contactor is on Y101. So we have to engage Y101 if we want our motor to run. And so what I'm going to do is, we know if we're outputting our start command that we configured here on rung 1 and it's latched, well, we know that Y005 is going to be on if we want our motor to run, right? So we can just configure that to turn Y101 on. And so what I'll do is I'll put a normally open contact that's Y005, and the output coil that fires is Y001. Okay. So there's probably more sophisticated and possibly better ways to do this, but this works, and this is something we need for this program to run. So now that I have this set up this way, this should work. Okay. This should allow us to run the motor. So I'm going to download it to the PLC. Okay. Let me go ahead and do a runtime edit. I'm actually, I have the e-stop pressed in, so it's kind of okay to do a runtime edit. And you can see here that e-stop contact is engaged. And so we're in a pretty safe state. Okay, so I'm going to switch to my other screen now. And let's scooch the camera down so you can see the motor again. Okay. Hopefully I don't blow a circuit again. So what I'm going to do is reach up and I'm going to take the e-stop off first. Okay. So that's good. And then I'm going to hit the increment button. Okay, so my counter counted up. But I haven't hit the start button yet, which means that my motor isn't actually going to run. So what's happening is right now, this math block is actually writing an output, and it's causing an analog signal to be output from that analog out card on the PLC, and that's being written into the VFD. And actually, if we look, well, never mind. It's not, because the VFD isn't in run, it's not taking that value. But we haven't hit the start button yet, so nothing's actually started. So now I'm going to decrement that counter. I'm going to change your camera view again. And I'm going to hit the start button. Okay. I don't know if you guys heard that ka-chunk, but there's a nice hefty thump that happens when you do that and the contactor gets pulled in. And then the status light on the VFD changed. Okay. So now I know my system's happy. I think everything's good to go. Change back so you can see the motor. And I'm going to go ahead and I'm going to increment that counter 1. And look at that. She lit up my motor. So you can see here, my sensor is getting tripped every time this motor rotates. My motor's set to 10% right now, so it's a nice leisurely pace. Everything's looking good. So I'm going to increment up again. And I got a question here. Is there a way to test code without being connected to the PLC? No, there is not. And so that's a serious problem we've run into due to the current quarantine situation. So I was actually going to talk about this a little bit later, but now's a good time to address this. So one of the things we can do is I can actually pass control of my system to somebody, and they can click around and make changes in the code, and then they can tell me what to do in the physical world to the panel, what buttons to push, and we can kind of let you guys get some hands-on experience with the controller that way. I know this isn't really great. It's kind of it's just an unfortunate fact of the situation in which we find ourselves. So going forward, starting next week, I think what I'm going to start doing is telling you ahead of time what we're going to work on, or you can come up with your own stuff that you want to work on, and have you guys prepare ahead of time a little bit, maybe write some code that you want to test out, and then let you guys drive in that way. And I know that's super unfortunate. There are some ladder logic softwares that have simulation suites built in so that you can basically test code without any physical hardware. Unfortunately, as far as I know, Click doesn't offer that. So that's where we're at. If you guys are interested, we can also work out some supplemental time where outside of our regular meetings, where we'll fire all this up in the same way as we have it right now. And I'll just basically turn it over to you guys and hang out in the garage, and you can tell me what to do. And we can let you test code that way. So if you're interested in that, email me and we'll work out some times. Maybe we can do another when to meet to figure out what's a good time for everybody. So that being said, we have 13 minutes left. So does anybody want to try with a remote takeover right now to write some code that basically monitors the speed of this motor using this sensor? Okay. So let's take a vote. Do you guys want me to try to do that right now in the 13 minutes we have left, or would you rather save that for the next time we meet?
I mean, you can work through it, but it'd be cool to see if we can figure it out on our own.
Okay. Anybody else?
Ooh.
What was that?
It's like, yeah.
Yeah. Okay. So it sounds like nobody has a super strong opinion one way or another. I'm just going to talk about what you would need to do to make that work. So the first thing is you need to figure out where that input signal is coming from that sensor. And so if you look on slot 2 here, there's all these external quick connects. And so right now I have that sensor wired into X201. And what we'll do is we'll go ahead and write in a normally open on 201, and we'll have that output to Y001, which is just a red strobe light. And I'll go ahead and drop. Whoop, what was that? Nope, wrong button. I'll drop that code into the PLC. Okay. I have the wrong input then. Wonder if it might be 202. Bear with me here. See, the code isn't the hard part. It's figuring out what you wired where. There we go. Okay, cool. So, so you can see in the code, that's cycling, and then you can see, I guess you can't see on the camera right now. Let me pull up the camera view. You can see that light's flashing on and off, and you might be able to hear there's a super annoying loud clicking sound in the panel. And so the reason that that clicking sound is happening is because that output that the light is wired to is a relay contact. And so there's actually a physical relay on the PLC that's clicking on and off really, really fast. And so if you were to actually be setting this system up in real life, you would not want to use a relay contact. You would want to use an optical contact that has no moving parts, because if you were cycling a light like this all the time, you would eventually burn that relay out, because you're just cycling it over and over and over really, really fast. And so if you do this, you know, it might take a year, it might take 5 years, but eventually that relay contact is just going to burn out, because it's not really intended to cycle fast like this all the time. So another fun fact to keep in mind, that's a total tangent and not really super important to what we're talking about, but good information to have. So in order to save our poor relay, I'm going to hit the stop button and kill it. Looks like I got another question in the chat. How do you fix that problem? Can you clarify? Can you get on your microphone? Oh, what Bill was talking about? So that's an interesting problem. The way this software works, for our purposes, you're actually not going to have to worry about that. So let me talk about how to configure the counter first, and then I'll come back to your question, Amandeep. So essentially what you're going to need to do is, now that you know what that input is, it's X202, you're going to set that up on a counter. And you're going to set that to be the input point on a counter. I'm going to set this counter to 10,000 right now, just as a placeholder value. Okay, so what this does is, this basically every time this X202 input fires, it'll increment the counter by 1. Okay, and Amandeep's question was, how do you avoid having this trigger the counter multiple times? And the answer is that actually what these counter blocks look for on the input is they look for it to cycle. So they don't just say, oh, this input is on, and I'm going to count up every PLC scan every time it's on. It actually looks for a change of state in this X202. And so basically every time that X202 goes high and then low, the counter counts up. You can get a little bit more fancy with this by using the differential contacts. And so the positive just means that when the state changes on, it'll count. And the negative means when the state changes off, it'll count. But you honestly don't even need to do that. The way this software works, and I've tested this extensively, is the counter block is looking for a change of state on this X202. And so you can actually just use a normally open contact like this. We'll go ahead and change it to a differential contact, just because that's a little bit more sophisticated, but to be perfectly honest, it doesn't matter. Okay. So now you have the ability to count up, right? That'll let you basically start accumulating counts of how many times has my motor spun. But that's not in and of itself enough to figure out how fast my motor's spinning, right? Because there's a time component to motor speed. It's revolutions per unit time. Usually you count that in RPM, right? Revolutions per minute. So the other part we're going to need is a timer, which is just another block in here. and that's going to count up to a certain certain value. So you got to select you got to select the memory bit for this. So we're just going to use T1. And then you got to select the set point for this. And this is an integer. And I do not remember what the max value for an integer can be off the top of my head. But it's fine. It can be really big. So we'll just set this to let's see. So you can set it to be in units of anywhere from milliseconds to days. I highly recommend leaving it in milliseconds because it gives you a higher level of resolution. Okay. And then you're going to set some value in the set point. So right now I'm just going to set that to be 10,000 milliseconds, which is the same as 10 seconds, right? And what that does is it fires this output contact when it's done, right? So when this accumulates to 10,000, it's gonna trigger that output, and then it's gonna stay on. And so you need to set up a way to reset this to start back at 0 when that's done. And then you should probably also do the same thing with this counter. Have it reset when it reaches 10,000. You want to reset that back to 0. And then what you're going to do is you're going to take these two values and you're going to do some math to figure out, based on the number of counts and the accumulated time, how fast this motor is spinning. Okay. And you're going to want to have that set up so that these reset every certain amount of time. Because if you don't, the memory bits that are accumulating for each one of the timer and the counter block are going to eventually fill up, because there's a limit on how much there's a limit on the size of integer that you can store in these memory registers. So I know that's kind of vague and non-specific. I want you to think about how to program this so that so that you can calculate the RPM of the motor based off that. So feel free to contact me with any questions during the week, and I'll actually just assign this as a homework to be due Monday. So we'll come back around and revisit this on Monday on how to do it. So going forward for the rest of the quarter, I think I'm going to try to structure it in this way where we talk about something on Wednesday. We end with call to action, something for you to work on in between now and Monday. And then we come back around on Monday and revisit it and try to get it working. And I think we'll just keep cycling through that for the rest of the quarter. So that's where we're going to end today. Does anybody have any questions?
Sounds good.
Very excited.
All right. So just a little bit more background on this. Basically, what we're programming right now is a very simple encoder. And so there's a specific hardware module that basically you clamp onto a shaft, and as that shaft spins, it sends a signal to the PLC that the shaft is spinning, and it gives it a number of counts. And so most of them are set up to where you might have 1,000 counts per rotation. And so what you do is you use that signal to figure out rotational or linear positioning. So rotational of the motor, which if it's hooked up to an actuator or a conveyor belt or something, you can then calculate linear positioning of that actuator or of the conveyor belt. So what we've made is a super unsophisticated encoder, which is basically 1 count per revolution. And so if we were to, let me bring over the camera again real quick. Change my view again. So right now, we just have one little flag off of this motor. If we put another flag off the top of this shaft, then the beam would get broken twice per second, right? And you'd have a 2 count encoder. And you could do it with 4 flags. Probably because of the physical limitations of this system, the most we're going to get on here is 4 flags. But if you guys are interested in that, once we get the base code working, I can go ahead and add more flags onto this shaft, and we can edit the code accordingly. So cool. I'm going to end it there. Any questions? You guys make me feel like I'm screaming into the void. Not a good feeling.
No question, sir.
Okay. Thanks for the feedback. I have a question for you. Does everybody feel like they understood what we did here today?
I think more or less I get how to use the click programming software. I just gotta play around with it to make sure I can actually reproduce by myself, you know?
Same.
Okay.
Yeah,
for sure.
it makes sense so far.
Okay. I know it's super difficult because you cannot in live time test your code. That's a huge problem we're fighting against. So if you're interested in setting up more sessions to just play around and like literally just turn on lights and stuff, just to get more comfortable with this, email me. We'll set up a time and make that happen. Because I think that's really important for getting a feel of how this works.
I have a kind of random question. Is it possible that the scan time lines up with the rotation such that you miss like all of the scans, all of the counts?
That is a great question. Based on field data of when we did this last quarter, no, it's not a problem.
Cool.
That is absolutely a concern when you're doing this kind of thing, and you have to basically test and validate. And so the way we're doing it is we're just sanity checking because we have a ballpark number that we know these rotations should be at. Oh man, sorry, excuse me. And so we're just sanity checking it, and the value last time we did this last quarter, the value is really close to what it should be. But that's why they actually, so those encoder modules, you need a special input card to take the encoder input, and those are configured specifically so that they don't have that problem of the scan time not picking up the signal. So
Okay, cool.
that is a really good question.
Thank you.
Welcome. Cool.
Could you say one more time really quick why you added in that third rung there?
The Y05?
Yeah, that one.
Yeah, so let me show you physically. So this, and I'm sorry I haven't done this yet. It's partly because I'm scared and partly just because it's going to be super time consuming. I need to go through and do a video where I do a build breakdown on this panel and explain what everything is and why it's all wired together, because I think it'll help y'all and your programming making sense of this stuff. But basically this right here is a motor contactor, and it's the wiring, basically the wiring from the VFD. This is the output to the motor. This is wired into the top side here, and then it comes out the bottom and out the panel to the motor. And so basically all this contactor is it's two big metal plates that chunk together, right? And then it's spring loaded. So if you don't have an input signal to it, they're separated and there's a physical gap. Okay, and so that motor contactor is wired to Y101. And so when Y101 is fired, it sends the signal that makes that contactor chunk together and lets that electrical signal travel out to the motor. And the reason, well, there's multiple reasons to have that. But a big part of it is just, it helps physically protect your VFD internally. Your VFD will actually get burned up internally if you don't have that, from my understanding. I'm not an expert on this stuff, but it's important to have that. It also basically just lets you have another level of control, because as you can see here, if you don't have this rung in your code, physically that signal can't get to the motor.
What's Y005 again?
So Y005 is our run command to the VFD. It's an output from the PLC to the VFD that says you're allowed to start, right? And so on this first rung here, we configured it so that when you press the start button, like so, you can't, never mind, you can't see it. When you press the start button, Y005 is lit up and it's telling the VFD to run. And so we basically just hijacked that signal, because we know if this output is on, then we're trying to run the VFD. And so we're just going to use this Y005 to light up Y101 and engage that contactor.
So you can't just directly engage the contact. There has to be like a signal.
So we can actually. What we could do is just delete, just have this rung. Whoops, not that. We delete this. So then rung 3, basically this would just, this rung would always energize as the PLC is scanning, and it would always fire that output, right? Generally speaking, this is something that you do not want to do in PLC programming. Because what that means is anytime the PLC is on in run mode, that output is energized, no matter what. And you have no way of programmably or physically interrupting that, short of just pulling a wire. So, best practice is to have something engaging that bit. And like I said, this is, ideally, you would have a physical switch, right? Like a toggle switch. Where the operator has to hit that switch, and that engages the contactor, right? And then they also hit the button, and that starts the motor. We have 4 buttons on this panel, so we're just limited on the total amount of user inputs that are available, and so. Because we need that up-down counter, we need the interrupt. We have one more button left for start, and so we're basically just ganging off of that signal.
Okay.
So that's the other thing is I'm going to send out an email about this. I want you guys to download the touchscreen programming software, and we can start playing with that, because what that lets us do is start programming virtual buttons and switches. And so we're not limited by the amount of hardware we have available. So then we could have a touchscreen switch that you have to hit that would engage the contactor, and then you'd have a separate start button.
All right, I gotta go. Thanks, John.
Yeah, sure thing.
For the touchscreen buttons, do you also make like electrical schematics and stuff like that for those?
No, not typically. I'm trying to think. Yeah, I mean, there's definitely like sequencing diagrams that you make, which is kind of, it's kind of like an electrical schematic in some ways, where you kind of just talk about the different run operations of the PLC. And you usually you control that with what's called subroutines. So you can see here, everything we've done so far has been the main program. So what you can do is program in subroutines. Whoops.
Is that kind of like a class would be in like Java or C++?
Pretty much, exactly. And so, or a function block almost.
Okay,
So,
function.
I mean, it's like a class in that like you can, well, this is where I'm going to show my ignorance in computer science. I think it's more, yeah, it's more just a function block, because you don't re-alias things in it. It just runs as it is. And so you can call it anywhere in your main program, and then it just runs the subroutine.
Okay, yeah.
Yeah, so just a function. So anyway, your main program might be like super simple, where you literally just have like 5 different rungs that call 5 different subroutines, and then your subroutines are your operational modes. And if you were doing sequencing diagrams for that, you would show whatever stimulus kicks you into those different operational modes, and that might be a virtual input from a touchscreen, and you would call it out as such.
Okay.
Sorry, I know I'm really bad at giving short and concise answers.
I have a quick question, Mr. John.
Yes, sir.
So since we're basically creating all these little functions using ladder logic without
Mhm.
being able to connect to the PLC, so not really knowing whether or not it would actually do what we propose it to do.
Yeah.
Are you going to be running these codes after we turn it in, or
Yeah.
like live? Okay, and letting us know if like giving us pointers on what's working, what's not working, or and stuff like
Yeah.
that.
Exactly. So my hope is that somebody turns in code that works pretty well, or is basically there.
Yeah.
And I can test it ahead of time and then let you guys know. Or you can, or we'll have you live test it.
Okay.
If not, I'll look at what you've turned in and kind of try to point out where the issues lie, where the
Yeah.
problems are. And then we'll go through, like on Monday, we'll go through a demonstration of how I would code it. And again, like my way is probably not the best way. Like I'm no expert on this stuff, so I'll find a way that works, but it might not be the same way you would do it, and the way you do it might work fine.
Okay. For sure, dog. Much
Yeah, man.
appreciation.
And seriously, like if you're to the point where you're like, I think this works, and you want to set up a time to test it out, just hit me up.
Okay. For sure,
Put a
dog.
dang shirt on.
No. I have a shirt on.
Do you?
Nice.
Oh.
Nice.
Sound disappointed. You're still recording this, aren't you, John?
Yeah, he is.
Yeah, it's
All right.
still recording. This is going.
Well,
on YouTube.
I'm just gonna peace out at that point.
I
right.
can cut it off if you want before I upload it.
No, you're good.
All right.
Yeah.
I have some interesting cameos in other classes that so it doesn't matter.
To anybody watching this in the future, feel free to tune out. Nothing important is going to be said after this point, or for the 5 minutes prior.
Just have like that disclaimer at the end of the video. Just the last minutes mean nothing.
Yeah, I mean, I'm not going to do that because I'm super lazy. So
Oh
I think
yeah.
they'll figure it out at this point. Hi, future people. Bye,
Hello.
future people.
Hello.
We are from the